Welcome to Measurement Uncertainty and Significant Digits. Let's start with a brief overview of uncertainty in engineering measurements. Anytime I make a measurement that's going to be used in an engineering calculation, for instance, I might measure length, or I might measure mass, or temperature. And I'd use a different device to measure each of these quantities, right? To measure a length, I might use a scale like a ruler. To take a mass, I would use something like a mass balance. To measure temperature, I would use something like a thermometer. And so my reading is potentially subject to uncertainty in the form of measurement error. And there's two different potential error types in my measurements. So the first one occurs when I have systematic bias in my measurements. So this is called accuracy error. So accuracy error is what occurs when the instrument that I'm using to record a measurement returns a reading that's different from the true measurement. So let's say that I'm taking the temperature of a fluid, and the true fluid temperature is 25 degrees C. And let's say I take repeat measurements using a thermometer that needs to be calibrated. So I would take a measurement 5 different times, and I would measure the first time, let's say 20.5 degrees C. Time number 2, I record 21 degrees C, then 20.4 degrees C, 20.7 degrees C, and a final time 20.6 degrees C. So this device is giving me a pretty similar answer time after time, within about a half a degree or so of each other, right? But the problem is that all of them are a little bit different from the true fluid temperature, which is 25 degrees C. So this is happening because my device has poor accuracy. And an error like this can be addressed, right? I can go and calibrate my thermometer to be more accurate. Now, the second type of uncertainty, precision error, right? This isn't something that I can fix readily. This is random error or noise that is surrounding the signal that I'm trying to measure. So after calibrating my thermometer to take care of that accuracy error that we just discussed, if I then take several repeat measures of the fluid temperature with my newly calibrated thermometer, so again, we know that the true temperature is 25 degrees C, and I measure it with my calibrated thermometer, and I get 5 repeat measurements. So these measures are closer to the true temperature of 25 degrees C. They're more accurate, but I've measured the same fluid at the same temperature 5 times in a row, and I've gotten slightly different answers every single time. Each one varies just a little bit from the other. So that degree of difference of one measure against the mean of all 5, that's defining the precision of the instrument that I'm using to take my measurement. So for example, even though my thermometer has given me temperature to the nearest 1/10 of a degree C, the precision of the instrument that I should report is only to the nearest 1 degree, because we have a little bit of precision variation within these repeat measures. So the concept of significant digits in an engineering calculation is related to the precision of engineering measurements that are applied in the calculation. So the parameter that has the lowest precision in an engineering calculation is going to define how many significant digits we can use to report a final result. So how can you know how many significant digits there are in a measurement? There are a few rules. So rule number one is anything that's not 0 is always considered to be significant. So let's look at an example. I've got 9.81. So here there are going to be 3 significant digits in this measurement. 9 and 8 and 1 are all non-zero numbers, therefore all 3 would be considered to be significant. Things become a little bit more confusing when there are zeros. So whether or not a 0 is significant is going to depend on where these zeros are relative to the non-zero numbers. So zeros that are showing up in between non-zero numbers are significant. So here I have an example of 1.0981. So there's a 0, but because that 0 is between a 1 and a 9, it's significant, and this number has 5 significant digits in it. Okay, what if I have a 0 and it is to the left of the first non-zero number? This would not be significant. So here, if I give the example of 0.0981, here we've got 3 significant digits. Because those first 2 zeros that are to the left of the 9 would not be considered to be significant. All right, last case is what if we have a 0 that is to the right of non-zero numbers? All right, so our zeros that are to the right of non-zero numbers, sometimes they're significant and sometimes they're not. So you know that when I write, 9.81, for instance, in actuality, there's an infinite number of zeros to the right of the 1, right? I just don't write it. I don't write a value in the thousandths place, then I would assume that value to be 0. So these assumed zeros are not significant. However, if I write the 0 like I have here, then they are considered significant. So for example, let's say I record the temperature of a fluid and I write the recorded temperature as 4.50 degrees C. In this number, there are 3 significant digits, even though the last of those 3 significant digits is a 0 located to the right-hand side of the 5. Another engineer reading my measurement would see this and understand that I used a thermometer that was precise enough to record temperature to the nearest hundredth of a degree C. If that's not true, if my device was only precise to the 10th of the degree C, then I should write this as 4.5 degrees C, and the significant digits would then be 2. So in regular life, it is really common to assume that most people will not take the zeros to the right as true estimates of a measurement. So for example, if I were to tell you that the number of people living in the Orlando metro area is 2,673,000, most of you would realize that the true measure could be plus or minus a few hundred people any given day when you factor in people moving in or out of the area, births and deaths. So you automatically discount the significance of those 3 end zeros and assume that this measure has a precision of 4 significant digits, right? The 2, 6, 7, and 3. But if I report this as an engineering measurement, including those last 3 zeros, then that would be a significant digit number of 7. So there's 2 different ways that you can clearly report the true precision of your measurement in this case. So one way is that you could put a line under the least significant digit that you intend your audience to consider significant. So if I put a line under this 3, that would indicate this estimate is precise to the nearest 1,000. But the best way for people to convey their true intention with significant digits is to use scientific notation, because that makes it very, very clear, right? So if I write this in terms of scientific notation, like this, then it's quite clear that there are 4 significant digits here. If you actually counted the number of people in the Orlando metro area and you found that it was exactly the 2,673,000, and you want to be really clear that your report is to a significance of 7 digits, then you can put a decimal after this last 0. That's another way of notating that this is a precise 7-digit estimate of the number of people in Orlando area. Okay, when we do engineering calculations, sometimes there may be several steps in a single calculation, and we do not ever want to round our intermediate answers. We complete the calculations in full, retaining all digits, and then we report our final results using a number of significant digits that's not greater than our least precise information that was used to derive it. So for example, let's say that I am estimating the density of a fluid, and I'm estimating this using a mass that was measured to 2 significant digits. Let's say I use my mass balance and I record a mass of 3.6 pounds of mass, and then I record the volume of my fluid to 3 significant digits, 1.25 cubic feet. And so then my answer is going to have 2.88 has 3 significant digits in it. If this is the final result of my engineering calculation, then I would want to report this to no more than 2 significant digits, because my mass was only found to 2 significant digits. So that's the least precise information I used to solve this problem. So my 2.9 pounds of mass per cubic foot would be the final answer that I would want to report. If I reported to a greater amount of precision than this, then it would be more precise than one of the measures, the mass that I used to solve the problem, and that would be incorrect. So thank you to the National Science Foundation for supporting this work under grant number 2335802. Great job reaching the end. Please reward yourself with a moment of Zen. I study fluid mechanics because I love water and healthy aquatic ecosystems. Whatever your passion is, I hope it motivates you to continue your study of fluid mechanics. Thank you.